Okay, class. Okay, so yesterday we learned about what we learned about double slit experiment. We learned about double slit experiment. Okay, so double slit experiment is a two source. Okay, it's a two source. The light pass through the two source, diffracted, then produces interference. Experience interference produces the pattern. Okay, so okay, this is the one we did. Okay, so today we're going to talk about another one. It's called diffraction grating. Okay, today's lesson is about diffraction grating. You can see down here. This is the appearance of diffraction grating. Okay, what is diffraction grating? Diffraction grating is actually this is what diffraction grating: a piece of glass or plastic which has 10 to 1,000 lines per millimeter. This is called diffraction grating, like shown here. Okay. Yes. So it's just a glass sheet got lots of maybe for 1 centimeter you can have 10 to 1,000 lines. Okay, you can have 10 to 1,000 lines. Okay, so you know double slit, you only have 2 openings, right? 2 openings. This diffraction grating has a lot of openings now. We say every gap is like 1 slit. That means you know double slit, when the light pass through, it spreads. Okay, interference happens. Interference happens here. Diffraction grating, the slits itself is like 1,000 slits, 10 to 1,000, 10 to 1,000 slits per centimeter of length. You know that means a massive interference happens. The source are thousands. They are interfering, produces a what do you call interference pattern on the screen, like shown in this diagram. Okay, so this is your diffraction grating. The diffraction grating got a lot of lines in between. Many sources, we say. Double slit only 2 sources. Diffraction grating is 1,000 of sources just within 1 cm of length. Okay, it's called diffraction grating. Okay, this is one appearance of diffraction grating. Okay, so this is your diffraction grating. This white color consists of the 1,000 lines per centimeter on it. What we are trying to do here, this is a laser pointer. This is a laser source. Laser was shined to the diffraction grating, and it produces the image on the board. These are the images on the board. Okay, formed by the diffraction grating. Okay, diffraction grating image is different from the double slit image because of what? Double slit image, the image will be like bright, dark, and bright, spots, equally spaced. The bright and the bright separation, if it's X, means all bright to bright will be X. The separation is the same. This is for the diffraction, for the double slit. But for the case of diffraction grating, you see on the appearance, the separation is different. The center to the first bright, let's say X, is not same as the first with the second one. It's slightly longer. It's not X. It's maybe more than X, of course. And the brightness, you see the brightness of the spot. The center appearance is more brighter than the adjacent one. Okay, and diffraction grating, the image is more brighter than the double slit. Why? Anyone? The double slit, the appearance, the image forms less brighter compared to the diffraction grating. Why? Because double slit only 2 source. It's only 2 sources. But diffraction grating is thousands of sources. That means, you know, your house window, like a house window only got a door, got 2 opening for the sunlight to come in. Okay, 2 openings, the double slit lah. Diffraction grating like a door with thousands of opening, thousands of gaps. So the light going to be more brighter, right? So the light going to be more brighter. That's why diffraction grating, the appearance is more brighter. Reason is what? The number of sources are a lot compared to double slit. Double slit only 2 sources. Okay, now you might doubt, what is the use of diffraction grating? What is the use? What we going to do by using this experiment? Same thing. We want to find wavelength of any light, as we did for double slit. Okay, but scientists found that finding wavelength by using diffraction grating it seems more accurate than finding wavelength by using a double slit. That's why people want to find wavelength, like scientists want to find wavelength, means instead of double slit, they go for diffraction grating. Okay, why diffraction grating give better, more accurate value for wavelength is the separation. The separation of the first bright and the second bright is quite far. Maybe it can happen in 10 centimeter distance, 10 centimeter distance. But for double slit, right, the double slit, the x value for double slit, you know, lambda equals to ax over d, the x value so double slit is quite small, maybe less than 1 cm. The x is like normally like less than 1 cm. Okay, you want a big x, you have to put a d very large. You need to put a d very large. D means what? The distance between the double slit and the what do you call, the screen have to be very large, maybe 5 to 7 meter more. You still get around 1 centimeter. So small measurement will lead to greater percentage uncertainty for the wavelength. So diffraction grating is quite accurate measuring the wavelength. Okay, so that is diffraction grating now, used for what? To find wavelength of light sources. Okay. Okay. So now, as I said, when a light passes through a diffraction grating, it's going to produce a bright spot at different point. Okay, bright spot at a different point. The theory they said is like this. The theory they said is same as last time. The center always will form a bright spot. Okay, center will form a bright spot, like a double slit also. Double slit. The double slit, the center point always form a bright spot. Why? What is the reason you learn? Because the path difference is 0 lambda. So as long as this is a crest, the path difference is 0. The center definitely going to be bright. Same thing for diffraction grating. For the diffraction grating also, although you have a lot of sources, but the wave when travel towards the center, okay, the path difference for the up and down wave, the second and the third wave, they're going to be the same. So they're going to have 0 path difference, 0 lambda, form a bright. Okay, center will be a bright for diffraction grating. Okay, and the following bright will happen at the side. Okay, following bright happens at the side. If you shine with a white light, same thing like happens for the double slit. Center will be bright, just a white light. Center will be a white light. But when it comes to the first order, this is called the first bright. The first bright, now we call first order. The name order is a special name given for diffraction grating appearance. Okay, the center bright we say 0 order. The center bright we call it 0 order. We use the term order for diffraction grating. 0 order means center bright. First order means first bright. Second order means second bright. So the first order will be a spectrum. The blue will be the closest. In other words, the violet will be the lowest and the red will be the furthest. The same reason. Big wavelength will diffract more. Will diffract more, so will appear further from the center. So you'll get the spectrum as shown here. Okay. So a white band is found to the center of constructive interference. It because all colors lambda travel from its slit, arriving the phase at the center. Therefore, no separation of colors. So all are in phase at the center. So therefore, they are bright. Path difference is 0. Away from the center, colors of different lambda diffracted through different angle. This is the point why spectrum forms. Different wavelength will spread at a different angle, form a spectrum. Mini spectra are observed in other fringes on both sides from red to violet. Red diffracted the most, so therefore it will be further from the center. Okay, and another one thing they found that the first order, let's say the spectrum spreaded for a distance of 1 centimeter means the second order, the size is found to be longer, like 2 centimeter or 3 centimeter. Okay, the spectrum longer. Okay, so for a diffraction grating, center will be let's say it's a white light, center will be white. The first order, let's say, happens here. The first order, second order even longer. Okay, so the third order, let's say, happens. There will be a chance of overlapping. A third order can overlap with the second order partially, can happen because the length of the third order getting longer and longer. Okay, overlapping can happen. I will be talked about this later. Okay, any questions from here so far? Okay, Ken, class? Ken, okay. Okay, so this is the light source we use to do the diffraction grating. It's hydrogen gas. Okay, hydrogen gas when produces light. And this is the setup. This is the setup for the diffraction grating. Okay, this diagram tells this is your diffraction grating. This is your diffraction grating. The diffraction grating got many types. Okay, on the diffraction grating here is written maybe 500 lines per millimeter. Sometimes you can write maybe 50 lines per centimeter. Got different type of diffraction grating. Okay, diffraction grating. Okay, so when you put more different lines per millimeter or per centimeter, the appearance is going to be different. What going to be different? The separation of the first order, second order are going to be different. Okay, we will see that in the next slide. So this is called the setup. This is where you're going to view. This is where the diffraction grating is placed. Okay, this is the source of light. This is a source of light. The light will pass through the diffraction grating. It's going to spread. Okay, it's going to spread here. The color is going to be spreaded. Center will be the zero bright. Okay, then what do you do? To see the first bright, this is your first bright. To see the first bright, this microscope you have to move around. You have to move around because you move in a circular track. You have to move around until you see a bright spot on this microscope. You will see a bright spot on the microscope. So you can measure the angle between first order and zero order and the first order. Okay, angle can be measured by using here. Here the angle is stated 0, 1, 2. It go one round for 360s. So you can read the angle up here and down here. Okay, yeah. This is called spectrometer with the grating. This setup is called spectrometer. Okay. Any questions so far? Okay, let me clear this. Okay, class. So this is the light, it shine, and yeah, this is how the appearance is going to be like if you put it on the light. Okay. So this student is looking at the light, and if you turn it, you're going to see a bright spot on the appearance. Rotate the telescope to see a few orders of fringes. It's a gas discharge tube, produces a color with a particular wavelength. Okay. So this is called spectrometer with grating. Okay. So the grating works based on this formula. D sine theta equals to n lambda. Okay, you have to know in depth about this formula. Okay. So what is D sine theta equals to n lambda? Okay, first, what is D? Okay, D is slit spacing. D called slit spacing. Like last time lambda equals to ax over d for the double slit experiment, the d here is similar like a here. Last time double slit, what is your a? A is your center to center spacing. This is your A. This is called slit spacing. A is the slit separation or slit spacing. Same thing works for the D. And so diffraction grating, let's say you got 100 lines per centimeter. Okay, that means the D value, the slit spacing is how much? Anyone? 1 centimeter got 100 lines. You got 100 lines, 100 slits in 1 centimeter. What is the distance between one slit to another? How do you find? 100 lines per centimeter. So 1 centimeter divided by 100 will give you the slit spacing. So in this case, it's how much? 0.01 centimeter. It's your slit spacing. Okay. So for example, here you see in the question here, there are 500 lines per millimeter on a grating. 500 lines millimeter on the grating. So n is 500 lines per millimeter. So what is D? D is 1 over n. 1 millimeter divided by 500 lines. So you get per line. So per line, how much is in millimeter? This is your D. Okay. So n lines for common term, if they say n lines per centimeter means what is your D? D is 1 over n, but the one should be 1 centimeter as 1 centimeter n. You get the D in terms of centimeter. Okay, so tell me 100 lines per centimeter, 500 lines per centimeter. Okay, you got two diffraction grating. One is 100 lines per centimeter, another one is 500 lines per centimeter. Which one has a smaller D? Anyone? Which will have a smaller D? Class?
What was it?
Can you listen to me?
Yeah. Yes.
Can listen to me, eh?
Yeah.
Just now the voice is clearer. Just now the voice is clearer.
It's the same.
Clearer. Oh, it's the same. Good. I get that. Okay. So let me go back. Okay. So if any problem, just inform to me. Okay. So what? D is slit spacing. So tell me, 500 lines per centimeter and 100 lines per centimeter. Which one has a greater, smaller D?
500.
500 will have a smaller D. Okay. So that is D slit spacing. Okay. Next, theta stands for angle of diffraction. What is the angle of diffraction? You see this diagram here. Okay. First we go for angle of diffraction. And this is your angle of diffraction. Okay. The angle of diffraction is this in this diagram. So from 0 to first order, and this is your angle of diffraction, theta. Okay. If you go for second order, if it's a second order, and this is your angle of diffraction. This is theta 2. Theta 2, this is theta 1. You see in this formula, you put theta as theta 1 when n is 1. Okay, what is n? N is number of orders. If you go n, you want to put first order, you want to put n as 1 means the angle must you key in here is the angle between the first order and 0 order, theta 1. Okay, when you put n as 2, let's say you put 2, n as 2, and the theta you must put here is the angle between the second order and the 0 order, theta 2. So it should be theta 2, and so on. If that appearance as third order, the n you put 3 means the theta you must put theta 3. Theta 3 means angle from the 0 order to third order, theta 3. So angle always measured from 0 order to that specific order. That's your theta. Okay. And n is the number of orders, which order you follow, and this is the lambda. Okay, this is called lambda, the wavelength. Okay, so when diffraction grating is used to calculate the wavelength, this is the formula they're going to use: d sine theta equals to n lambda. Okay, d sine theta equals to n lambda. Okay, so to find lambda, of course, d sine theta over n will give you the wavelength. So to calculate wavelength of light by using diffraction grating, what measurement you need to calculate? You need to calculate the D. You have to check the grating line. Check the grating. Check how many lines per centimeter or millimeter is stated there. If they write 500 lines per centimeter, so you can find the D. 1 centimeter divided by 500. So you can find the D first. And n depend. You see the telescope, the microscope, right? You see the microscope. Is your diffraction grating from the center. That's your zero order. So when you turn it to the right, the first time again you see a bright spot, and that's your first order. So you measure the angle. Okay. So the n you put 1, and the theta is the theta you measured by using a spectrometer. The spectrometer you place here, you can calculate the wavelength. It seems wavelength calculator is quite accurate by using diffraction grating. Okay, compared to what do you call double slit, because of the distance. Sometimes some lab they don't have mass spectrometer. So what they do, I go back. They use this setup. They won't use, if they don't have money, then they won't use this setup. They'll use this one, this laser beam. Okay, they use this setup. Okay. So from here, how they can measure the wavelength? How they can measure the wavelength by using this setup? Okay. So the same formula need to be used, right? What is the formula for diffraction grating? D sine theta equals to n lambda. Okay, n. Okay, if you view this is the first order. So n we go for equals to 1. Okay, n is fine. We can value the n. D we can get it from the diffraction grating statement here. Theta. How do you calculate the theta? How you can calculate the theta? Theta, the first order happens from the center. So yeah. Why again?
Hypotenuse.
Hypotenuse, good. The trigonometry, we use trigo. So you measure the distance between the diffraction grating to the screen, and diffraction grating to the screen. We measure this distance, maybe y1, and we measure from the zero order to first order this distance as maybe y2. Of course, we can measure the angle. The angle is what? The tangent theta equals to y2 over y1. Okay, we can work out the theta. Okay, so this is another way to find angle. If you don't have that spectrometer, you can use this technique. Okay, so the technique they use here, I told you this y2 value seems to be quite huge compared to the double slit. Double slit, the bright and the following bright, as I told you, is very small, maybe 1 centimeter. So lambda equals to ax over d. The x will have a greater percentage uncertainty. Changes of x over x. The x is very small, so the changes of x over x are going to be very big. So therefore, wavelength you calculated through that experiment is very big percentage uncertainty. So not advisable. Diffraction grating is quite good. Okay. Any questions so far? Okay. So let's proceed. Hope if the college open up, I can show you every apparatus. Practicals are pending. Okay, so I go back here. So D is spacing, theta angle of diffraction, and n is number of order, and lambda is wavelength of light. Okay. Okay. So now you see, another one problem now is the highest order. Okay, highest order. What is highest order? You see, when you use the diffraction grating, you move the microscope around, first order, second order, and you might see the third order. The number of order you're going to view going to be limited or unlimited? Is it infinite or going to be limited?
It's infinite, but it gets dimmer.
It gets thinner. You see, the theta 1 and theta 2, the angle get bigger and bigger. The angle bigger and bigger. So the maximum order you can see, the maximum angle you can turn the microscope is what angle? 90. Okay, so 90 is the maximum angle you can turn. This is the maximum point where you can see the orders. Okay, so the number of orders you can see is limited. It's not unlimited, it's limited. Normally, the the maximum order you can observe is barely I see 4. Never happen 4. Normally 3 is the maximum order for a visible light from 400 to 700 nanometer. The maximum order I think normally is 3. Sometimes can happen 4, but very rare. Okay, very rare. It depends on the D value. Okay, depend on the D value. So the orders is limited. In exam, they will ask, what is the highest order you can observe? Very famous question. They will ask, what is the highest order you can observe on the diffraction grating? So how do you find the highest order? The highest order. So D sine theta equals to n lambda. You are looking for what? Highest order. You are looking for n. You are looking for n. What is the maximum n? Theta you substitute as what?
90.
Yes, that's the point I want to tell you. Theta you substitute as 90 when you go for highest order. Theta you put 90, you can find the n. So the n you get, let's say you got 3.8. So what is the highest order you observe? Should be 3. Okay, don't round up, have to round down. Okay, if the n value given is 3.8 through the calculation, when theta you put 90, n gives you 3.8. The maximum order you observe is not 4, don't go for 4. The fourth order is not appeared yet. 3.8, only 80% of the fourth order, so not counted. The round down. So 3 orders is the maximum order you observe. Okay, so if n you got 2.9, so the maximum order you observe is how much? 2. 2. Round down the maximum order. So let's say you got a maximum order, n maximum you got, let's say is 3.3. So you go for 3. That means by using a diffraction grating, how many bright spots you're going to see on the screen? Center 1, 0 bright. 3 order means this is first order, second order, third order will appear here. Then down you get another first, second, third. So how many bright lines you're going to observe throughout? Total bright lines you're going to observe what? The maximum order is 3. That means up is 3, down is 3, center another 1. So altogether how much? 7 bright spot will be observed. Okay, 7 bright spot will be observed. If the maximum order is 3 times 2 plus 1. Okay, if the maximum order is 2, if n max is 2, how many bright spots are you going to see on the screen? Maximum is 2, n max is 2. That means first order, second order, that's it. So how many you have? 0 bright 1, first order, second order at the bottom. So maximum, all the bright spot you're going to observe on the screen is 5. 5 bright spot will be observed on the screen if the maximum order is 2. Okay, same thing. So that's the maximum order. If that's the maximum bright spot observed on the screen, times 2 plus 1. Okay, be careful with the exam question. If they ask maximum order, answer is 2. If they ask what is the total bright spot observed on the screen, if you got maximum order is 2, then the answer should be 5. Okay, can understand? Okay, now look at this question. For one example, there are 500 lines per millimeter of grating there. So n is 500 lines per millimeter. So 1 over n, 1 divided by 500 mm. So this is your D. This is your D. Okay, meter per line. So this much meter per line. This is in millimeter or meter? 1 over 500 times 10 power negative. Oh, this already in meter. This in meter. It's meter. So this in meter. This is your D. Okay, determine the number of image for 600 nanometer. They're asking what is the total number of image forms on the screen. So what do you do? You find n max. Okay, you find n max. So D divided by 600. D over lambda. You see D over lambda. D over lambda. Because theta you substitute is 90. Sine 90 become how much? 1. So D sine theta equals to n lambda. You find n max. So n max means it will be D sine theta over lambda, but theta is 90. So sine theta become 1. So equation tend to become d over lambda only. D over lambda only. So put the d and lambda. D is 1 over 500 times 10 to the power negative 3. Divide by lambda. Lambda is 600 nanometer. Here be careful with the unit. D is in meter. 600 nanometer is in nanometer. Change to meter. Can you tell me, sir, anyone, how much the maximum order you can observe here? Okay, please get me the answer for this. I erase this all. Get me the answer for this part. The D is this. This is your D. Can you find answer for this? So D over lambda. What is the maximum order you're getting? 1 divided by 500. The times 10 power negative 3 is on top. 1 times 10 power negative 3 over 500. That's your D. Okay. And divided by what? Divided by 600 times 10 power negative 9. Change to meter. It's also in meter. So anyone, what is the N max you get?
3.
3. Is there any decimals?
3.33.
Okay, got so 3.33. Therefore, N max is 3. N max is 3. So determine the number of image for 600 nanometer. So answer is what? What is the total number of image observed on the screen? So 3. So on top you have 3, and down also you will have another 3. Center is 0 bright, so altogether will be 7 appearance. 7 image will be formed on the screen, bright spots. Okay. Okay, these bright spots, we call construct maxima. We call it sometimes called maxima. Okay. These all are maxima. Maxima means, what is maxima? Point where constructive interference happens. In diffraction grating, minima is low profile. We don't care about minima. Minima is quite widened. Only maxima is focused in the diffraction grating. What is maxima? Point where constructive interference happens. Okay. So this is the formula. You now tell me. A student used the diffraction grating. He shined with the yellow light. Yellow light. Okay. He found the number of orders formed is maximum is 2. Okay. The student replaced the diffraction grating with another one, and he found that the number of orders still used yellow light. The maximum order found by using this diffraction grating is 4. Okay, tell me. First one, second one. Which diffraction grating has greater D? Which one has a greater D? Which one has a greater D? The first diffraction grating or the second diffraction grating? Use this formula. Interpret for me. Which one has a greater D? When D get greater, what happened to the angle for the first order? The sine theta is what? N lambda over D, right? When D get greater, what happened to the angle of the, yeah?
Shorter.
Get shorter, right? So that means when the D increases means the N max rises or drops?
Rises.
When D max increases means N max rises. Very good. Please remember this point. When D increases means the N max is rises. So 1 or 2 has a greater D. The 2 has a greater D because N max is 4. D is greater. If D is greater means, okay, one got 200 lines per centimeter. Another one got 500 lines per centimeter. The diffraction rating. When you choose a diffraction rating, these are the statements given. 200 lines per centimeter, 500 lines per centimeter. Can you tell me the 1 and 2 is one of them is 200 lines per centimeter, another one is 500 lines per centimeter. Tell me 1 or 2 is 200 lines per centimeter or 500 lines per centimeter? 2. number 2 grating as a rate of 200 lines per centimeter or 500 lines per centimeter?
200.
Should be 200 lines per centimeter. 200 lines per centimeter will lead to greater D. Greater D. Okay, so this kind of evaluation you have to do. When D get greater, so remember this point, the final point, remember, when D get greater, the N max increases. N max increases. Okay. Okay. So one question for you to do. Calculate for me. Get the answers for this question. D sine theta equals to N lambda. Yes, come on. Do the working. Okay, waves from monochromatic source pass to 1000 lines per millimeter. The angle of first order is 36 degrees. Determine the wavelength. So all of you must get this is the answer for it. 588 nanometer. You get 588 nanometer for the number 1. So number 1. So how do you do? D sine theta equals to N lambda. You are finding for lambda. Lambda is of course D sine theta over lambda N. So D is the problem. Sine theta we found as how much? Sine theta, the diffracted beam is measured 36 degrees, first order, 36 degrees. So theta is 36 degrees and N is 1. But D, how do you find the D? D is said to be how much? 1000 lines per millimeter. So what is D? 1 times 10 to the power of -3 over 1000. 1000. Yeah, this should be your working. If I put 1 times 10 to the power -3 means the D, what you need? I put it in meter. So the lambda you're going to get, the final answer will be in also meter. Remember, one important trap, the trap is the lambda and D must be same unit. Must be same unit. You put D in centimeter means your final answer for lambda also will be in centimeter. In exam, they purposely will give D and lambda in a different unit. Make sure if question asking for theta means the D and lambda must be key in the same unit. Okay, be careful. Okay, they purposely will give a different unit. Convert it to the same unit. Preferably be meter, both of them. Okay, so you get meter. You should get how much? You should get what? 588. So you should get 588 times 10 power -9 meter. 588 times 10 power -9 meter. Then you get 588 nanometer. So everyone getting this answer? I hope this is the working. You are adapting. Okay, so that's number 1. Okay, that should be the number 1. Make sure the unit same. Okay, 2. Determine the maximum number of high intensity fringes can be observed. Include the central fringe. What is the total maximum bright spot? High intensity fringe means the maximum bright spot, the bright spot observed on the screen. So whenever they say maximum, you look for N max first. So D sine theta equals to N lambda. So find the N max first. What is the maximum order can be observed? So D sine theta over lambda. So D as usual, put this value. Okay, 1 times 10 power -3 over 1000. But sine theta we know is we take it as 1 because 90 degrees. And lambda we take it as what? Lambda, the one you got it earlier, 588 times 10 power -9. Make sure the unit for D and lambda same. If not, it's going to be everything wrong. You get N max. How much you get? Anyone?
$1.7.
Okay, good. Thanks. So you get 1.7. Therefore, N max is how much? N max is only 1. Okay, N max is only 1. So how do you going to imagine the appearance? That means I draw here. That means the diffraction grating, only the first order has been observed. That means first order up there, down also first order. So center 0 bright also at the center. So how many appearance you see? Altogether 3. The answer is 3. You get 3 orders. The answer is 3 maximum in high intensity fringes has been observed. Okay. And the third one? Third one, yellow light or wavelength of this passes through the grating. At what angles will bright fringes be seen? Okay, this is lots of work. Okay, so they say the fringe, the diffraction grating one now shine with the yellow light. They want for every order of appearance, they want the angle. At one angle, the first order happens. At one angle, the second order happens. At one angle, the third order happens. We don't know how many orders are there. So you have to check one by one. Okay, so we go for first order. So how do you find the first order? Same formula, right? And so d sine theta equals to n lambda. So find the angle of the first order, sine theta 1, right? So n you take it as what? We just put it as 1. Wavelength you know already. Wavelength is 588. Change to meter. D also put it in meter. You can find theta 1. Okay, theta 1. 0 order happens at 0. This is theta 1. You should get theta 1 as 17.1 degrees. So everyone give a try. They get 17.1 degrees. So d sine theta equals to n lambda. N put it as 1 because you want to find angle of the first order. D and lambda we know already earlier. But make sure d and lambda same unit. Meter means both meter. So shift sign you get 17.1 degrees. Okay. Then repeat this step for second order. Second order, n you put as what? Put it as 2. Find the theta 2. So the theta 2 you should get. Okay, theta 2 you should get 36.1 degrees. And the third order, okay, third order, theta 3 you get 62.1 degrees. So according to the answer, looks like only a third order. If you try to look for fourth order, what is the calculator shows you? How do you know the fourth order is never appeared? Through the calculation. The theta you get, I think when you do shift sign, you get math error. Okay, you get a math error. That means when you put sine theta, finally it's a sine theta 1. Okay, the sine theta you get more than 1. You get more than 1. Sine theta normally is less than 1, right? So if you get a math error, that means that order does not appear on this setup. So theta 4, I think the calculator should show math error. That means it shows theta 4 doesn't exist. Okay. So I believe all of you get 17.1, 36.1, and 62.1 for first, second, third order. Okay. Any questions so far from this slide?
Sir.
Yeah.
Can I find the N max first, just to know how many orders are there for
yeah, can. Yeah, you want to make it like that also again. And max check is it 3, so then you go, you have to go for 1, 2, and 3. Okay. Okay, before we go to this, finish this, I need to add something on top of this. Okay. Okay, you see, diffraction grating again. Okay, if you have a diffraction grating, okay, let's say you shine with a white light. You shine with a white light. Okay, what you're going to see? Center is going to be a white. It's going to be a white. Then the first order, what you're going to see is a spectrum. You're going to see the spectrum. So this is the violet. This is the red. Okay, and you further up, you can see a second spectrum. And if you go to the third spectrum, I told you can overlap. They can overlap. Overlap can happen. Question they can ask about overlapping and overlap. Tell me, listen carefully. Tell me, is it third order of red overlap with second order of violet possible, or third order of violet overlap with second order red possible? Which is possible? First one possible or the second one possible? Third order of red overlap with second violet possible, or third order of violet overlap with second order of red possible? Which one can overlap here? You see the age? Which age is overlapping with which one? The second order age, the top age of the second order will be normally what color?
Red.
Red. So second order of red most probably can overlap with the third order of what? Violet. Yes, remember, second order of red can overlap with the third order of violet. Okay, when they overlapping, what quantity same? The angle going to be same. Both will have the same angle. Okay, when overlapping happens, the angle going to be the same. Okay, so in exam they're going to ask like this. They're going to ask like this. They're going to say that, okay, the second order of violet overlapping with the third order of red. Okay, find the ratio of lambda red over lambda violet. Find the ratio of lambda red over lambda violet. After you measure the angle, the angle of overlapping is found to be theta. Find the ratio of lambda red over lambda violet. How are you going to find this? By using diffraction grating formula. For the red, which is the third order, use the diffraction grating formula. It will be what? D sine theta equals to n lambda, where D is D of the diffraction grating, sine theta, the theta angle we measured here, and n going to be how much? 3, because it's the third order. This lambda going to be which lambda? Lambda red. Okay, this is the first equation for the red. For the violet, violet happened in the second order. So how's the equation going to look like? D sine theta going to be second, because second violet happens in the second order, and going to be lambda violet. Okay, so this is the clue. See, when overlapping happens, both D sine theta is the same for both of them. Both crosses the same diffraction grating, so D same. Both will make the same angle, so theta same. Therefore, D sine theta for both of them is the same. Therefore, we can conclude what? We can conclude that 3 lambda red is same as 2 lambda violet. This is what you should make a conclusion. Therefore, from here, lambda red over lambda violet, you can conclude the ratio is 2/3. This is how the answer going to look like. Okay, understand? So whenever overlapping happens, in your mind, please remember the angle have to be same. They will ask question about the ratio of the wavelength. The ratio of the wavelength. If I want to put it in a common term, if I wanted in a common term, okay, common term means, let's say there is a violet, second order of not red, they put the wavelength lambda 1 overlapping with the second wavelength lambda 2. Okay, lambda 2. Lambda 1 of the second order overlap with the lambda 2 of the third order. Okay, find the lambda 2 over lambda 1. So in your mind, you must do what? 3 lambda 2 must be equals to 2 lambda 1. This is what you need to conclude. because d sine theta is the same. You see here, 3 lambda red must be equals to 2 lambda violet. So from here you can find the ratio of the wavelength. Lambda 2 over lambda 1 is 2 over 3. Okay. So big wavelength will have a shorter order, a longer order, a greater order. Big wavelength will have a smaller order. A small wavelength will have a big order and overlapping happens. When overlapping happens. Any question from this slide? This explanation? Okay, can okay, so we go to one question. Okay. So one pass here. About diffraction grating. Okay, this question. Page 4, question 29. Give me the answer. So d sine theta equals to n lambda. Okay. Give me the answer for 29. Okay. Tell me your answer through WhatsApp. Hope everyone give the same answer to me. Okay, anyone got the answer? Can send me. Okay, so all of you giving D. All of you got D. So the trap here is this 43 degrees. 43 degrees. How much of angle you supposed to use here? Because this 43 degrees is angle between what? Is it angle between two second orders? That means the second order here and the second order here, the angle between them is 43 degrees. But according to the formula, you want to key in this formula, this theta is actually theta angle from the order to the zero order. So the theta is supposed to key in is 43 divided by 2. So if those who done that, then you should get the correct answer. Do you get D? If those who divide 43 divided by 2, then should be the correct answer. Okay. So D is how much? Where's D? D not given. Monochrome light, normally on a diffraction grating, the 2 second orders are 43. What is the spacing of lines? So find the D. We're looking for D. So D sine 43 divided by 2. N is second 2, and lambda is 590 times 10 to the power of -9. I want to change to meter. So therefore D I'll get in meter. Then you change back to now micrometer times 10 power -6. So you should get the answer. Any questions from here? No questions. Okay, class. So we're done with superposition. This is the last part, but I'm still will be spending 1 hour on Monday to do the questions. Okay. So now please try questions from this wave paper. Now you can do all the passes ready. Okay. On Monday, the first hour, please come out with questions if you don't understand. If not, I'll ask some questions before we continue with the last topic for your semester exam. Okay. Okay. So please do these questions. Superposition is one of the difficult topics in AS. Okay, if you don't have questions, we can stop. No questions. Okay, thanks. See you then on Monday.